Well, good morning, folks. We'll go ahead and get started, and I know a few more folks will be joining us shortly. I'll go ahead and open us up in prayer, and then I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course. I pray that the material will be clear. Pray that they will see the linkage between what we're studying and the ultimate area where they'd like to be working. Pray that you would help them as they're working on getting internships and working on getting their first job after their graduation, as they're getting into those times when that's coming. Lord, I also pray that you would help each student with their spiritual formation, Lord, that they can be getting a better understanding of Scripture, something that they can take with them the rest of their life, and also the theological concepts in which we want to be drawing from that. And also give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, what I wanted to talk about today was to continue to be thinking in terms of we're finishing up pretty much with our work on assembly language, but in terms of our project work. But I still want to be continuing through that as we get into a little bit more details, thinking about the instruction set and the assembly language. And so I'm going to be spending some time going over that by thinking about a couple examples. I introduced the Raspberry Pi last Thursday, and I'm going to continue to be talking about that. And I have two references on assembly language that I posted in Canvas, and wanted to spend a little bit more time going over that. And depending on time, I also then wanted to be getting some more hands-on work with our Project 3. And there's a sample project that's fairly basic that I think could be something that we could be working on in class, and I'll reserve that towards the end. And plus, if anybody else would like to be sharing their assembly language code, that would be great. And so let me go ahead and just begin to walk through a couple of things in that regard. I'm going to go over to for the lecture notes, because I'll be coming back and forth to this a little bit. And so we've spoken a couple different ways and in different layers of how we can be doing the doing instructions in assembly language. And so we've talked about the number formatting, how we do computer arithmetic, and the digital logic. All of that is stuff that we need to be mindful of. And so if you think of, like, if we're doing the subtracting numbers one from another, one way to be doing that when you get into the hardware is you take one number, you take the two's complement, and then you add it. So we can have an adder and then a simple modification, or something that you could do in the arithmetic logic unit, we can be doing another function. So those are the kind of things that we're starting to get a little bit more insight as we get into these details. And so then we need to be thinking about how are we going to format that information. And so that will be another thing that we'll be starting to come up with the material that we'll cover today. So okay, so first of all, let me share some information from the two textbooks, ebooks that I mentioned for assembly language programming. And so the first one is Cuss Worm. And so he has this book on modern ARM assembly language programming, and it's actually fairly helpful in the type of information that it covers. It gives a lot of information. And so I'm just going to highlight a few things and then get into the details on some of those. And so the three main areas that he has in his book is he talks about a 32-bit architecture. And if you think of just do a survey through some of the things that they have here. You'll see basic arithmetic, addition, subtraction, multiplication, and division, how we handle integers. Those are things that are talked about. Doing things with the stack and how it is architected in a ARM version 8 architecture. How to be dealing with integer arrays, integer matrices. And so just like any architecture, these types of things need to be defined. We have gotten an introduction to thinking about floating point architectures and doing floating point operations. They deal with that. It's actually a couple chapters that they talk about that. So single precision, double precision, these are things that you want to be thinking about when you're focusing on things at a very low level, like what is happening for assembly language. And then we have this other thing, this SIMD architecture, and just to give you a reminder of what I mean by that, and I'll come back to this in our in Cusform as well, but this was a way of how you can be dealing with multimedia. So it's a single instruction, multiple data. And so that's the thing that's starting to come up here. And so there's a whole section on SIMD architecture. So how you can allow for a multimedia for a 32-bit ARM version 8 architecture. Then I'm just going to skip down. Then when they do the 64-bit architecture, and so what actually are some of the distinctions between that and a 32-bit architecture? So you'll see some parallel between what was going on in the earlier chapters, and then they do the SIMD type of things for the 60-bit architecture. So that's a kind of in a nutshell what they're talking about in the text. And so what the contention for Cusform is that in a lot of situations that doing things at the assembly language level may not be necessary, but when you're talking about this multimedia type of operation, this is still an area where you can actually improve performance by doing things at the assembly language level. And so that's one of the observations that he makes in his introduction. So he talks about that he's going to be using a Raspberry Pi with Raspberry Pi OS 64-bit, and the things that he's going to be using for an ARM basis for doing the coding that he has. He mentions the various types of individuals that might find this resource useful. Software developers who need to become familiar with the ARM version 8 platform, those that are doing SIMD multimedia accelerators, and folks like us in this course of those who are students and are trying to get familiar with what things work, how things work at this level of an architecture. So we went through the table of contents, so I don't need to go over this again, but I'm just going to skip down to an appendix. So I actually showed you some examples, and I'll actually show you a compiled example of actually running the code using this hardware platform. And so I have a Raspberry Pi at this vintage. So one thing that they mention is the version, the Raspberry Pi, the current operating system version is version 5, and so it's actually a little bit more current than what they have here. Since I actually have mine plugged in, I can't actually show you my Raspberry Pi, but this is basically what it looks like. And so sometimes they say it's like a credit card size computer. You can have either a fan that you put on top of the processor, or it's called a SoC, a system on a chip. You have you actually have two HDMI ports. You have an Ethernet connection. You have USB ports. Those are your inputs and outputs. And they also have these pins. And so these are the things that look similar to what we have with our Arduino. And so there are some ways where you could either choose to do some of these projects with an Arduino or a Raspberry Pi, but this is a little bit more software intensive. And so that's one of the reasons why we're not doing it that way. So they use a Broadcom SoC system on a chip, and the ARM Cortex A72 is a processor that's on there. And so we'll come back to that in a few minutes. They use the GNU open source tools. And so I'll show you a little bit of example of that if you're not familiar with that. So it gives you the details of how to get things up and running. But if you actually get a Raspberry Pi that has the operating system already installed on it, you won't have to deal with a lot of these details. And this is all of the things that are expanded out. I've actually put a link for the GitHub for the repository of this. And so in each chapter, they have multiple modules that you can compile and then run. And so all those things are readily available. So you use the GNU Make to actually compile these things, and then you have an executable that within Linux. So you just have dot slash and then the name of the executable, and it'll run. So what they do is they have a C++ module, and that C++ module actually calls an assembly language routine that is run within the C++ environment. So that's just a couple of things that I just wanted to be pointing out from a top level sense. And let me go back now to chapter 2 is the first one that they actually have some code that they have here. And so let's go ahead and just do this first one, and I'll pause and see if there's any questions. And so the first thing that they talk about is addition and subtraction. And so here is how that is done. And so in the future, if you were going to be using an assembly language project, having a hardware accelerator by implementing it in assembly language may be what you would do. And so this is the name of the subroutine that is actually was created in assembly language, and this is how you would call it in a C++ program. So it's an external, you pass information to that. So there's 4 parameters that are passed into that. And that's how we see this being utilized. So here is when it's actually in use. And so we define values, and then we print the results. And we actually have 2 examples of what we do. So this is the actual assembly language routine here. And so this is the way that it's done in this sense. Depending on what type of module that you're using, what type of IDE, the slash would not be what you would use for a comment, but the way that they're doing it here, and the GCC tools just works just fine. And so we just have a couple basic commands, add, subtract, and we then return this. And those are the commands that we actually have here. So let me go over to my Raspberry Pi environment, and I told you that using Rio VNC, I actually remote log into that. So this just gives me, within my same environment, I'm able to share with you multiple computer instances with our course. And so I'll be using this, and also I've shown things with my Surface as well. So there's one command, it's called lscpu, and this is the information that it provides. There's a couple CPU or hardware monitor utilities that are available. Over the last couple days, I was trying a couple things, and so this is the information that it dumps out here. And so for the architecture, it's ARM v7.1. It uses the byte order little endian. And so let me go back and show you what that means from a couple points of view. First of all, let me do it this way. Okay, the main thing of what CusWorm is using is the ARM v8 microarchitecture, and the ARM Cortex A72, which is this. This is the chip that it's using. So it's actually a chip from ARM, and that's put on that SoC, system on a chip. And so we have some information here about, well, what's inside it. And so it has 4 cores. It has the CPU, the SIMD engine, so that is that multimedia thing, a floating point unit. So maybe you could be thinking of that like a GPU that's associated with a core. And then it actually has a couple of caches here. So L1 cache and L2 cache. This is what we have in the Raspberry Pi that I'm showing. They also show here something that's a little bit more powerful, and it actually has 3 caches, an L1, an L2, and an L3. And from our discussions with buffering and caching, that would be something that you would have some familiarity with. It also talks about this pipelining, and now that we're getting into this next area with this material, we'll be starting to think about how things are operated, and having a pipeline, this fetch, execute, we're going to be getting into more details, and hopefully that will be instructional to you as we go. So there's this little endian versus big endian, and see, I think that's down here. Yeah, here it is. This is the one I wanted to show you out of CusWorm. And so this is the little endian byte ordering. And so this is dealing with how you're going to be looking at things. And so you can either have it Q15 going down to Q0 if you had a quad word. Half word, it would be H1 and H0. So you either have the big endian or the little endian would be the two possibilities. And so the quad word, it's reverse from what would be in the little endian. The double word is reversed. The word is reversed, and the half word and the bytes are the same. And so that's one of the things that they're talking about there. And we really didn't talk about it in details, but there was a chart from Tuesday that I went over that included this. It was talking about this endian type of support that's available in the ARM architecture. And this endian is the order or sequence of bytes in a word, is what that's referring to. So we can see that there's 4 CPUs, there's 4 cores. It's a little endian. We have some information about its architecture. We have the model name. We have what the maximum CPU frequency is. So it ranges from 600 to 1500, the minimum to the maximum. And so those are some things that are interesting for us to be considering. So let me go ahead and go to chapter 2. And we're going to be doing this first module here. And I'll just So I'm going to this folder. And I'm going to go to this first module. So I already did this, but I'll do it again. If I wanted to actually make this and or compile it, I just type in the word make. Okay, since I already done it, everything's up to date. Now all I have to do is run the executable. So as dot dash CP/CH02_01, and it produces these results. So let's go back to the textbook to show you that it produced what we expected. So back in chapter 2, I'm sorry. So we have the C++ program. We have the actual subroutine that's written in assembly language. And I don't think it shows oh, it does. And so it shows the test results here. And so if I was to show both of these at the same time. So we can see it worked as expected. And so this is another way in which you can be doing some assembly language and seeing, say, maybe a construct that would be a little bit more likely that you'll be using in the future. So let me pause for a second to see if there's any comments or questions on what I shared.
For the adding and subtracting, is that whole numbers instead of decimals?
Yeah, let's look at that. I believe it is adding whole numbers at this point. The the yeah, these are just integers at this point. Okay. They will be talking about some of the more complicated types of things in the latter chapters. Let's see. Any other questions or comments that people have? Okay, well, one of the things I want to say thank you to Avery for finding this. So some of you are finding that the Mars MIP emulator had a little bit of a difficult to follow IDE. And so one of the things that you can do now is actually use VS Code as an alternative way of doing your coding. And so so let me just do a quick roll call. Are people familiar with using GCC tools? Just you can do a thumbs up if you have used them. And then I'll let Ryan show his stuff. So Austin's familiar with it. Anybody else is familiar with using GCC tools? Okay, so a lot of some, at least just from the polling, maybe half of you or so have not used it before. I really got exposed to that when I got really interested in open source software. So either at the operating system or application. So I'll come back to that in a few minutes. Go ahead, Ryan. Well, thank you very much. Well, since David asked this question, I'm going to try and walk through using this Raspberry Pi to show an example of using floating point operations. One of the things I'll encourage people to do while I'm doing that is to pull out your Arduino kit and I'm going to show a sample project for a simple digital input. And so you can give this a shot and we could easily straddle this over a couple of weeks. And so that would be perfectly fine for that to happen. So I'm just going to get to the directory first, and then I'll show you things from Cusworm to help to bring it to light. Okay, so in chapter 5, this is the first of 2 chapters that deals with floating point architecture. And so remember, you have an exponent and a base that we need to be dealing with when we have something like this going on. And so here we can either have half precision, single precision, double precision. So the significand, that's the number, and then you have the exponent. This is the one that's to the right. And so you can see it doesn't spell out the number, but you can see that the number of bits that are used for the exponent is getting larger, and the number of significant digits in the significand are getting larger. So it's laid out here. So 16, 32, 64 bits. So the significand goes from 10, 23 to 52 bits. The exponent goes from 5, 8 to 11 bits. We have a sign bit. And so those are all things that we have here. So this is the overall program for this first example. So for this first one, it only has a C++. So we'll start out with that just to give a sense here. So all you have to do here, there is actually something in here called a make file. So when I do this make, this gives the information of how it's going to compile the C program. And if it needs things from the include and data, it's going to give that information of how to get to those sources. Okay, so it worked. And so we produce the results and it matches what we have here. So you could say this is like a baseline. See if there's, okay, so I don't think there's anything else in chapter 5, but let me go to chapter 6 now. Okay, so this is chapter 6. For the first module. Okay, so we'll have some C++ and some assembly language portions here. So I'll do the make. And then do the execute. Okay, well, let's look at the textbook and see what it lays out here for this first example. So we're dealing with single precision arithmetic, and so in the previous chapter it laid that out. And so we're going to be doing a conversion from Fahrenheit to Celsius. And so the name of the routine that we're going to be doing in assembly language is convert F to C and convert C to F. So it's all put into one routine. And so we have you could say that this could be like a hardware accelerator. We're trying to do a GPU accelerator for a math function. And so we're just trying to have a quick way of doing these conversions. And so we're doing this in assembly language. And as we had seen before, here is the way how you make sure that you're able to call a compiled assembly program and execute it into C++. So since this has a wrapper with C++, um, trying to see where they declare these different values. And so, David, you might want to take a look at this, and you can just send me an email. We can begin to play this out a little bit more. It may actually be handled by the type of command that you use here. So single precision, double precision. And here we see we're calling out that these are single precision. So this may be the instrumental thing that we need to be thinking about. So this might be some useful information. I'm going to open up Mars and go to the help feature. Yeah, so here you have a double. This would be a double precision. Maybe someone will see it faster than me. I'm trying to see if there's a single precision if it's listed here. Could be that this is not exhaustive.
The dot float is the single precision floating point.
Okay, thanks. So this could also be indicating a slight difference between what we have in the Mars emulator and what is in this ARM. And so they're both assembly language, but there may be a little bit slightly different in their conventions. So that's something I just haven't been able to run to ground yet. So, but I know Avery mentioned it. So at least in terms of a self-contained environment, that you know exactly what's implemented in here with the instructions, the directives, the syscalls, all that. So that's what we have for that. Okay. So David, that's a little bit more information for you. And if anybody does actually get this textbook, please let me know. I was hoping that they would have an ebook version of this that you guys could utilize from the library, but I didn't find it that way. There was through another academic affiliation that I have, I was able to get a copy that I was able to download, but it's copyrighted, so I don't have permission to share it, especially since it was at another institution that I got this resource. So, but that's a first of two resources that I mentioned. The other one, this is something that's freely available from ARM. And I thought it was interesting when I looked at the overview of how they do this is assembly language is a low-level programming language, just one step above the processor's native language, that is machine code. So they give that as a basis for thinking about it. And I'm trying to figure out, they had another comment here. And assembly language instructions are very basic in comparison to those of higher languages. And says it's often impractical to write a whole program using assembly language. And actually even goes a little bit stronger, that they would almost argue that there isn't that much except maybe for learning to get familiar with machine language. And so if some of you found out as a result of doing a little bit of assembly language that you hate it, chances are you won't have to deal with it. So you can be thinking about that. But the other resource that I mentioned, Cussworm, I was showing you that he was mentioning for SIMD, for multimedia. There still is places where it could actually be beneficial. So if you wanted to get a chance, at least what ARM thinks about assembly language, this is another resource that you can be seeing. It's going to be trying to point you to their tools, which are paid for tools for development. So I wasn't steering us in that direction. I wasn't able to, didn't have the time to see if they had an academic tool suite that would be free or low cost. But that was another thing that I wanted to mention. Okay, any questions about that? All right, well, let's go to now think about our Arduino projects for a few minutes. We're almost out of time, so I'll just introduce this, and this will be something that we can be talking about next week. And so just for ease, that I actually have an Arduino Uno that I mentioned. And so the project that I loaded up and was showing you, I'll just give you a heads up by letting you see the serial plotter. And so the program that I had loaded up before is still running. Hey, give me a second. I'm trying to figure out why it's not working. Okay, well, I'll just leave that. Maybe because when I opened up the second script, this is the thing that was causing the issue. With your Arduino kit, it likely had a CD that was associated with it. And on there will be some sample programs and things like this, things like that. And so just to give you a sense, I've gotten several kits. And so the first year that I did, I got, there's an Arduino CD. And so so they had something called a button. And so it's a fairly simple way of how to be putting together a project. And so having something really well laid out for starters, if some of you have not had any experience with this can be quite helpful. And so this is a real basic type of setup that you can have. And so it's going to have a push button, an LED, and your Arduino, and those are going to be the main things that you have. And it introduces some of the components. And so this is a push button switch. And it actually, you either can actuate it, and so A and D would then be connected to B and C. So that's what the switch does. And so I could be hooking up more than one thing if I wanted to. That would be the basis of what that switch is. So this one, except for folks that are on the engineering side, this may seem hard to wrap your head around, but here is the Arduino, and it's actually telling you what pin you would be connecting this LED to a resistor to the switch, and that switch goes to ground, and it also ties into this specific pin. So this first one is D2 and D10 and ground, and those are the three things that we need to make sure that we plug in to make this work. This is probably more helpful, especially in the beginning, that these are the pins that you would connect to. So literally you have three components: the switch, a resistor, and you can see it's red, red, yellow, red, red, brown. That's actually indicative of how much resistance is in that resistor. And so you hook up this, you could actually hook this directly up. Okay, so this first one, you put the ground to this one. And so for this one, all of these ones in green, they're all connected to that one pin. All these are connected together. So if you put a wire there, then all you need to do is put a wire there to one side of the switch. Remember, these two are connected together and these two are connected together. And then we have this D10. That's what's here. And so it has a squiggly line. Or that's what this is the D10. Then we're also going to be putting a ground to this side of this resistor. And then we have the LED, and then we put the other end to pin number 2. And so what I would like to have people do is by next Thursday that you create this circuit with your kid. And so let me just do around the room. Can people give me a thumbs up if we can go ahead and agree that we'll have everybody get this configured by next Thursday? I got a couple of thumbs up. Okay. And what I'll do is I'll load this up on Canvas, and this is the actual thing that you want to be loading into your IDE, and then you want to be loading it up into your Arduino Uno or whatever one that you have. So this also shows you the code, but as part of the zip that I'll be sharing with you, it will also have that spelled out. So you have this PDF, and then it has a code, and it just this digital inputs is all that it is. And so I know for some of you, it's you've never had to deal with hardware before, and I'm trying to help you take that next step of breaking the ice and getting familiar with this. And hopefully this will be a simple, easy thing for you to get your head around. We're going to be doing 3 sub-projects for this one like we've done in the other ones. And so for some of you, especially, this is really pushing the envelope of what you've done. You could actually just vary this a little bit, make this your first project. Maybe instead of a red LED, you might try a green LED or something like that. But those are just some ideas that I just want to be having you think about. Okay. So we've covered a variety of information, and I'll continue on these tracks. We're finishing up with our assembly language, but I'll be coming back to that a little bit more as we start to think more in depth about CPUs. Thanks again to Avery for giving us another way of doing the assembly language coding. We've also now are going to be pivoting more towards the Arduino kits and getting a chance to see how that works. And I have several Arduino projects that I've already configured, and I've already mentioned a few of those, but we'll start to get into some more details as we go from here. So with that, let me pause and see if there's any comments or questions. All right, well, God bless you all. I'll look forward to seeing you again on Tuesday, and reach out to me if you do have any comments or questions. Okay, take care.
Thank you. Have a good one.
Thank you.
Just double checking. Oh, it's any questions? Anything I can do to help? Avery, anything else I can help you out with? Okay, well, you guys can reach out if you do. Take care. God bless.